Good morning, everyone. Myself, Vivek Kumar, and I welcome you all to today's talk that is organized by Department of Physics and Astronomical Sciences, Central University of Himachal Pradesh. Today, we have with us our visiting scholar, Mr. Vivek Kumar Jha, who is doing his Ph.D. in extragalactic astronomy from Aryabhatta Research Institute of Observational Sciences. He is involved in outreach. He has played a key role in outreach activities at ARIES, and recently he has launched a portal called Cosmic Varta to promote astronomical research for public or for common people who have no background of the astronomy as a course. And today he will share some interesting work that he has done during his PhD that will help you understand the most powerful objects in the universe. So by not taking much time, I would like to call on stage our today's speaker, Mr. Vivek Kumar Jha, who will deliver his talk titled with Glimpse into the Heart of Quasar using light echoes as a tool.
Okay, so thank you, Ritesh, for the introduction. And good morning, everyone. My name is Vivek, and I'm a PhD student at ARIES and registered at DDU Gorakhpur. I'm a visiting student here at CUHP. So the title of this talk is Glimpse into the Heart of a Quasar using light echoes as a tool. So I'll try to explain what quasars are and how difficult it is to image their inner regions, and then what are the kind of methods that we can use to understand the innermost regions in these powerful objects. So before I go into the quasar phenomenon, I would like to show you a few images. So if you look at this image here, so this is an optical image of a quasar. But if you ignore this thing, streak of light here, so it looks like a star itself, right? So this was the initial idea of these objects. So what happened is that people, when radio astronomy started in 1940s and 1950s, so they started imaging some objects in the radio, and they found that the radio position of some objects, they match exactly with the positions of galaxies. So people were confused because at that time people did not know that how luminous these objects can be, and so how luminous these objects can be, and what is the connection between the radio and optical wavelengths in these objects. So people were clueless at that time, and then when multi-wavelength astronomy developed, so people started to observe them in different wavelengths. Like you see the same object here seen in X-ray. So you see this prominent streak of light. It's quite visible here in X-ray wavelengths also. So this is a multi-wavelength phenomenon, the quasar. And this object in question here, this is known as 3C273. So this was the first ever known quasar in the history of extragalactic astronomy. So what happens is that I'll give you just a brief of history here. So the radio position was known for this object, and people could image it in optical, as you can see here, but it looks like a star itself if you ignore this thing. So when people took the spectrum of this object, so you see the spectrum, it had quite broad emission lines, right? And if you calculate the velocity of these emission lines by using the Doppler method, so it's like thousands of kilometers per second here. So stars cannot have these high velocities, right? So then there was a hint that these objects might be extragalactic. And now if you look at the H beta emission line here, so the wavelength is around like 5800 or something like that. But H beta wavelength is 4861 angstroms. So this is redshifted. So then people put a hypothesis that maybe this object is located very far away, and due to the redshift effect we are observing H beta, and if you look at H alpha here, so this is also redshifted. So this is how, so people interpreted it, in 1963, so Martin Schmidt, he discovered this spectrum, and he interpreted that this object is maybe that it could be explained that this object is located at a redshift of 0.15. So this work he published in Nature, and if you look at the title, it's quite interesting. A star-like object with a large redshift. So they were not pretty sure whether these are galaxies or these are something else. So he said that these are star-like objects. And now if I go a bit further inside the history, So in 1917, people could image some nebular objects because the astronomy was quite developed at that time, and people could observe images like this. But they did not know that these are galaxies. They thought that these are some, maybe there could be some planetary nebulae. There can be some planets. I mean, like nebulae, they look like this, and this is pre-Hubble era. So people did not know that extragalactic objects may exist. So they thought that these are planetary nebulae. Then in 1943, what happens is that Carl Seifert, he observed few of these nebulae, and he found that the unusually broad emission lines are there, like thousands of kilometers per second. But how can the planetary nebulae have these broad emission lines? So then the breakthrough happened in 1963. The image that I showed you in the last slide, that he interpreted, Martin Schmidt, that this object could be interpreted as having as located at redshift 0.15, and he said that this can be a star-like object with a large redshift. But what happened is that in 1964, people say that it is a quasi-stellar source. Why quasi? Because they were observed in radio and different other wavelengths also, which is very uncommon of stars. Hence, they said these are quasi-stellar objects. Then what happened is that if you look at the luminosity of these things, so they are like, 10 to the power 40 to 10 to the power 48 arcs per second. And our sun is like 10 to the power 32, 33 arcs per second. So, 10 to the power 15 times brighter than the sun. So how can a star have this much brightness? So this was a big problem, and in 1973 it was proposed that maybe these are quasars, and maybe these objects, they are powered by accretion of matter onto the supermassive black hole. And this theme is what we are going to discuss in this talk, that how accretion of matter it happens onto a supermassive black hole, and how it plays out, and how can we measure the accretion disk sizes. Now it has been more than 50 years since this discovery. And so far we have gained pretty much insights into the innermost regions. If you look at this video here, so this is the same object, 33273 with a jet, and we have some artistic impression of zooming inside the innermost regions. So if you zoom in a bit further here, so the understanding is that this kind of object is there, and if you look at the length scales here, so this is the innermost region here, and this is like a few kiloparsecs from the innermost region. A parsec is 3 light years, kiloparsec is around 3000 light years. So this range is around 3000 light years from the central supermassive black hole. And the red thing that you see, this is envelope of dust inside the innermost regions, and the dust is basically, it's obscuring all your these things. So now if you have a face-on view here, so if you are looking that in the sense that the dust is blocking your view, so then you cannot have a view of the innermost regions. While if you look at the edge on from this point of view, so if you are here, so then you can clearly see the innermost regions. So suppose now this object, so this 33273, this is in between. This is not a face-on, this is not an edge-on, something in between, because you can see the jet here. So say zoom. Oops. So if we zoom in a bit further, so we were here. Okay. So this is the So now if you zoom in a bit further, now you see clumps of gas here, right? And this is, now we are talking about some parsec scales, some milliparsec to parsec scales. So now if you look at the clumps of gas here, so these basically is known as the broad region clouds. And you see, if you move closer towards the center, the faster your rotation of this clouds is. So this is because of the Kepler theorem that the nearer the black hole you are, the faster you are rotating. So this way, and this region is basically responsible for the emission of all the emission line that we saw in the spectrum there, because of the temperatures in this region. So now further inside, if you zoom in, so this simulation does not go inside inner than that. So further inside we have the accretion disk, and then at the center we have a supermassive black hole with a mass of around 10 to the power 6 to 10 to the power 9 solar masses. So a million to a billion solar masses black hole is sitting inside the heart of these objects, right? And now if you look at this is the general picture that we have. So this is the torus that you saw, the red colored dusty thing here. So it basically obscures your view, as I told. So if you look at, so now these galaxies, they are divided. They are divided into multiple characteristics. But for the time being, for this for the theme of this talk, I'll just talk only about type 1 and type 2. So type 2 are the one where this torus is blocking your view, and type 1 are the ones where the torus is not blocking your view. So if you are looking at the galaxy from somewhere here, so the observer will see the type 2. While if you see someone from here, so observer will see the type 1 galaxy. So only type 1 galaxies have the view of the broad line and the innermost regions, and type 2 will have your torus blocking the view. So now, since I'll be talking about the accretion disks in AGN, so the discussion will focus on type 1 AGNs only, because type 2 will have some obscuration, which we cannot take care of. Okay. So since 1963, the population of AGN, it has exploded. If you look at this plot here, so this is the Julian date convention for time we use in astronomy. So this is like Now it's 59,000, something like that. This is modified Julian dates. So for the past 10, 12 years, so you can see the explosion in the number of quasars so far. This is all thanks to the Sloan Digital Sky Survey, because they release their data publicly, and this is their generation. So the fourth generation, you see, we have around 700,000 quasars known so far from this Sloan Digital Sky Survey. Now, why are they very important? So you see, they are discovered up to redshift 7. So redshift 7 is the location which is 1 billion away from the Big Bang, 1 billion year away from the Big Bang. So Big Bang happened 13 billion years ago, we assume that. So it's like 12 billion years ago, we are talking about these things. So object is detected at redshift 7. So basically you can probe the universe, which was 12 billion years ago. And other thing is that they are detected in multiple wavelengths. You can observe these quasars in gamma rays, X-rays, optical, IR, radio. They are detected in all wavelengths, and because of their detection in multiple wavelengths, we now understand that there are different physical processes involved. So I mean, these are very good astrophysical laboratories to understand all your physical models. Okay, so this is again the innermost region. Now I just put this slide again because some sort of this revised kind of thing. So now this is the torus again, and now if you look at the this red region here, so this is the innermost accretion disk. So you have the center supermassive black hole. The matter is accreting onto the black hole. The innermost region will be emitting in higher energies, and the outer regions will be emitting in lower energies. So this is a kind of thing that red is denoting higher energies here, and blue is for cooler regions. So these are like very close to the supermassive black hole. These are subparsec regions, and they are really nearly impossible to resolve even for the nearmost objects, because even the nearmost quasars, the innermost region is like subparsec. So subparsec is like the size of our solar system itself. So you have to resolve our solar system at a distance of million light years from here. So it's not easy based on from looking from the Earth. So this is just a physical processes. So this is the spectral energy distribution of these objects. So on the X you see this energy here. So this is frequency. So 10 to the power 10 hertz. This is in log wavelengths. So 10 to the power 10. So this is basically we are talking about radio. So here you come in IR. This is your optical. This is your X-rays, and then you move towards the gamma rays. So as you know that there are multiple elements involved there. You have the accretion disk, we have the corona over the accretion disk, we have the disk wind, the matter flowing outside the accretion disk, you have emission lines from the BLR, as I told, you have the dusty torus. So all these things contribute to form the composite acids of these AGNs. And if you look at the innermost regions again, so in the innermost regions we assume that the reprocessing of X-ray wavelengths, it will be the X-ray, the photons arising in the X-ray wavelengths, they will be reprocessed into UV and optical and IR into further. So this is one of the accretion modes that we understand. However, the physics of AGN accretion disk, it is not understood clearly because the field is quite young so far and it has not been explored quite much. Now, okay, so how do we probe it? Since we cannot image the innermost regions, so how do we probe it? So for this we have some indirect methods. So one of these is the variability. So now if this AGN, as I told, that they are detected in multiple wavelengths, so they are variable in almost all the wavelengths. Now if you look at one of the images here, this is for one of the AGN, I think this is one of the type 1 AGNs here. So you look at the X-ray wave light curve here. This is variable in X-ray. Now you have the variability here in UV also, ultraviolet, and this is H beta emission line in optical, 4861 angstrom. And you see this variability correlated. X-ray, you have some peak in X-ray, then there is similar peak in the UV, and then you have some peak in the optical wavelengths. So this is why we assume that a disk reprocessing is happening. So basically the photons that were being energized here in the X-ray, so they are being reprocessed through the ultraviolet, and then they are being reprocessed through the optical. So now if this assumption is true, so then we can estimate the size of these regions. So which I am coming to in the next slides. Okay, and this is a simulated light curve for IR. So this is not the real one. Okay. So to assume correlated variabilities, we have one technique known as reverberation mapping. So what happens is that if you look at the model of the inner region, this is your supermassive black hole, this is the accretion disk, this is your broadband region here, the pink thing, and the yellow thing you see, this is a torus here. So now the farther you are from the black hole, the higher wavelength you have. So you have X-ray in the innermost regions, optical in the medium regions, and then you have this IR here in the torus. So now, basically, as I showed you the light curve in the last slide, so now if this variability is driving this variability, and in process this is driving this variability also, so what happens is that you have some sort of a driving source here in the innermost region, and it will drive the variability in all the regions, all the nearby regions, right? So now, what happens is that, so suppose you get the photons from here, then you get the photons from here, and then you try to see cross correlate all these photons. Okay, the light curves. We call this thing we call light curves. I mean, based on the time and the flux. Okay, so what happens is that if you get a light curve from this region, and then you get a light curve from this region, and then cross correlate the two, so what happens is that you will find a lag between these two. Why? Because say photon is originating from here, then it will be passing through this region, and this is like milliparsec thing. So I mean, it will take some days from here to here. It will take some days because we are talking about some. See, this is 10 to the power 5 Schwarzschild radius, so it will be like parsec, some parsec scale, right? So parsec is like 3 light years. So this will take some days from here to here, right? People who have done this torus reversion mapping, they have found that the size of torus to be around 35 to 40 days. So basically, photons are originating from here, and they take around 40 days from here to here. So how do? You get a light curve from here, you get a light curve from here, you cross correlate these two, and then try to estimate the lag. If you get the lag of some days, so then you can see multiply that lag with the light travel time, because the signal will travel at the speed of light. So you multiply that with the speed of light, and then you get the R. R is basically your delay between these two regions. So this is one of the methods to resolve these regions in spite of their very closeness, very unresolvability from the Earth-based telescopes. Right. So reversion mapping has been quite popular. It has been used to estimate lags between the accretion disk, different wavelengths in the accretion disk. It has been used to estimate the lags between this is inner region and this broadline regions here. And it has also been used to estimate the lags between your inner regions and the dusty torus. And yeah. So now I'll be talking about accretion disk. So the same technique of reversion mapping applied to the accretion disks in AGN. So I'll be focusing on this technique only. So now AGN accretion disk is here. So we assume that the disk is surrounding the supermassive black hole. What happens is that the black hole is like 1 million to billion solar masses. So it will be accreting mass at a very high rate. So what happens is that the mass will have some angular momentum. It will fall into the disk, and it will from the black hole it will form a disk because of it has to lose the angular momentum from there. So this way it heats up the disk, because if you are moving like this, so your energy is being released, and this is why it is. Yeah. So this heats up the disk, and now this accretion is responsible for the enormous luminosities that you get in these objects. And now we know that the innermost region of disk is quite complicated. So one of the models says that the disk might have a corona at the top, and this corona is basically radiating in X-rays. And now basically you see all these lines here. So there is quite feedback going on between the disk and the corona. And then the corona is basically reprocessing all your photons originating in the innermost regions, and then these photons are being reprocessed in different wavelengths there. Right. So coming to the models of this accretion disk. So the simplest model that we can think of is the Shakura-Soinev standard disk model. This was proposed in 1973, and basically this assumes that disk will be composed of multiple black bodies, like you see in the left here. So I mean, it consists of annuli. So there will be many annuli at different wavelengths, and various wavelengths will have various temperatures depending on the Wien's law and all those things. And if you try to derive the temperature of the disk here, so it will be governed by this equation, which depends on your black hole mass there, the accretion rate of the black hole, and then you have the size at which you are talking about. So the temperature at the size R will be given by this equation. And now temperature can be converted into the wavelengths based on your Wien's law. And so if you have the temperature converted wavelengths, now if you observe your disk in different wavelengths, so then you can get the interband lags. The same technique of reversion mapping is applied here. So now this looks like something like this. So innermost region will have hard X-rays. So hard X-ray is basically the photons originating with energies having greater than 2 keV per electron, per photon. So this is hard. Soft will be like 0.2 to 2, less than 2 keV. So this is soft X-rays. Then you have the far UV, and then you have the UV optical, similar disk reprocessing model that I talked. So the photon originating here is being reprocessed into this, and this is the black body disk. So basically, if you observe your disk here, then you observe your disk here. So basically, you will get some lag because of this disk reprocessing in time, and this lag can give you the extent of this thing, right? So if you do multiple band monitoring, so you will have correlated lags, and these lags can give you the size. Okay. So the first project that I applied this technique in detail was this AGN Storm project in 2015. So basically what happens is that they picked up the AGN NGC 5548. This is one of the most commonly studied AGN so far. And this campaign, it has published 13 papers so far and still going on strong. So what happens is that they observe, you see, this is the X-ray here, HST. HST is basically Hubble Space Telescope. So it observes your AGNs in X-ray and UVs from space. Then you have Swift. Swift is another telescope which is observing UV and optical. Then you have UBGRI, these are optical bands. So this you can do from ground-based telescopes also. So basically what happens is that they combined HST, Swift and ground-based monitoring to generate these many data points. So see, so these are different wavelength data points. So X-rays will have these wavelengths. This is in angstroms, 1000, 2000, up to 9, 10,000 you can go from ground-based telescopes. So now, if you observe this thing and now you cross-correlate these light curves, and then you get the lag with respect to this wavelength, right? They obtain the lag with around 1200 angstrom wavelength, and now you see. So the farther wavelength, farther you are going, the lags are increasing. So this is again explanation of this thing itself, right? So the farther you are going, so light will take some more time to travel. So obviously you expect that this area will have larger lags as compared to these areas, and these were larger lags as compared to these areas. So this is what we assume that in discrete processing, and this is what has been a very remarkable result from this project so far. But the thing is that it has a very big caveat. So now you look at this one. So this cyan line that you see here, so this is what this Shakurov disk model is predicting, and this is what we are getting. So although this is and this is 4/3, so Shakurov is predicting that this disk sizes will be scaled by 4/3 based on this equation. So you see the R is 3 here, T is 1/4 here. So this T will be proportional to R by 4/3, something like that. So it is following 4/3, but the magnitude is quite large. I mean, it should have been this if the disk model was being followed, but it is quite large. However, it is following 4/3 scaling here. So this is a very big problem that they obtained from this campaign. Okay, so then multiple agents have been observed using the same technique. I mean, this is a very expensive and very resource-intensive technique because you have to get time at HST, Swift, and ground-based telescopes simultaneously. You have to monitor them. This is very, very difficult to do. So this technique has been applied to only around 10 sources so far because of the complications involved. And even the people who are involved with in HST teams, people who are operating the HST telescope, STSI people, they are having difficulty time getting this so far. Right. So how can we move further then? So what we can do is that, so now you see this UGRIZ you are getting from ground-based surveys only. So suppose we ignore this thing and we follow this thing only, UGRIZ. So all this scaling will be true here only also. So if you have multiple wavelengths, so this should be true for your ground-based observations also. So because the SS disk is predicting your lags as 4/3 for all the bands. It's not that it is only in the X-rays or the UVs. So what you can do is that you can do ground-based monitoring. And now suppose you skip the space-based things and come to ground-based things. So what happens is that your sample size increases significantly. So you know only 10 sources have been observed so far using HST Swift. And if you look at the ground-based surveys so far, so Penstars is a survey. So the Jiang et al. They have published researches for 40 objects from one source. Then the SDSS, this Humayun et al. They did for 35 sources. Then again this dark energy survey people have done 23, 13, and 40 sources. So you see 10 sources using space-based telescopes and more than 100 sources. Same thing using ground-based telescopes only. So this is another way forward because based on only 10, because the population of AGN is 700,000. So now you're talking only about 10 sources. So obviously to populate the sources with this kind of study, you have to follow ground-based surveys only. Right. So in this context, we also did some study, and the physical thing is that okay. So once you obtain the disk sizes, so what is the relation with the black hole mass? Because if you look at the equation here, so you assume that this black hole mass should have some relation here, right? So what is the relation with disk sizes of the black hole mass? Then we have to find that what is the relation of the disk sizes obtained here with the luminosities, because luminosity is also a parameter which depends on your AGN parameters, the black hole mass and the accretion rates, and yeah. So based on the results here in Humayun et al., so they have not found very strong correlation between the disk size and the black hole mass here. So this is the tau, this is a proxy for the disk size, and this is the black hole mass here. So you see that the relation is not very tight, although they have tried to fit something, but this is, you cannot say that this is some sort of a correlation or anti-correlation between this. Same thing with luminosity also, that we do not have a very strong relation with disk size and the luminosity. So this is a problem. I mean, this should have some relation. So in this context, we try to do this study here. So when I came here, I was just analyzing the results from this project. So this is a result from the ZTF survey. So this is basically an all-sky survey operating from the Lick Observatory in California. And basically, they observe the entire sky every third night. So every 3 days, we have one or two data points. And this survey has been running since 2018. So I analyzed data till 2021 only. So we have good cadence for 3 years. So for 3 years, around 1,000 days, we have 3 to 400 light following data points. So it's an all sky survey, and it gives you the data in 3 bands, right? So for this, we chose a sample having greater supermassive black hole masses, and we found that this sample can have wide range of luminosities and the wider supermassive black hole masses. And then we try to see whether the disk size that we obtain using these light curves, whether they relate with the black hole masses obtained in the literature or not. So this is the plot that we get. So this is the G2R. So we have 3 bands here. So G2R lags are plotted here, and G2I lags are plotted here for the same source. So you see again, G2R lags are shorter, G2I lags are a bit larger. So same disk reprocessing is true for this also. So then we also model the light curves to estimate a disk size directly at some fixed wavelength using this equation. So now if you look at the disk sizes here, so you have the distribution for this thing, because we analyze this using Bayesian method, so we get a distribution, and then based on distribution only we can calculate the uncertainties, right? So now this is a very important plot from our work. So what happens is that this is this disk size prediction here, this red line that you see here. This is what we expect from the Shakura-Sunyaev disk, and these are the results that we get from our modeling of the light curves. Though there are huge uncertainties because data quality is not very good, and we are covering only 3 bands, and like you see, Storm they cover around 22 bands. So obviously we'll not be expecting very precise measurements here. But even if we talk about the upper limits, so even then the disk sizes they are not quite following the Shakura-Sunyaev disk as expected. So this is also a very good result. And then this is we try to put our lag estimates in the 4x3 context. So the black dot that you see, this is the SS disk prediction, and the green one is that what we get from the modeling, and these are the interband lags that we get. So for most of the sources, like this one, it's quite matching. So this can be an anomaly. But for most of the sources, we see the prediction is this, the black one, and the green one is what we get. So again, here also we get the same thing, that the disk is following 4x3, but the disk size, they are not as expected from the Shakura-Sunyaev disk. Right. So then we try to plot our supermassive black hole masses with the disk size with the supermassive black hole masses, and the blue point that you see here, these are our points from this study, and here also these are the predictions with different accretion rates. So what happens is that your black hole is accreting better at some rate. So if you increase the accretion rate, your disk size will increase, right? So this is why I plotted 3 different accretion rates here. So this is dimensionless, 0.01, so like 1%, 10%, and then 100% of that intent limit. So even these 3 regions, so our disk size obtained here, especially in this regime of low supermassive black hole masses, is quite high as compared to the predictions. So this is also a result which we did not expect. We were expecting that disk size will be a bit smaller here, but then what we can do. So yeah, so the prediction from Shakura-Sunyaev disk is like that. So R should be proportional to MBH 2/3. So this is a relation that is plotted here based on SS disk. So the disk sizes are, larger, and then we plot with the luminosity here. At 5100 angstrom we calculated the luminosity, and then here also we do not find very good correlation here, very weak correlation between the disk sizes and the luminosities in this sample. Yeah, so this is the final thing. So what happens that what can we do next? So we do not find any significant correlation between disk sizes and the supermassive black hole masses. So whether this is true for this sample, because this sample covered only 20 sources so far in the study, so whether this is true for a larger sample or not, this we need to check. Then what happens is that you see your disk sizes, they can be dependent on the accretion rates. So is the disk size for low accreting black holes and the high accreting black holes, is it a bit different? So this we can also test. And then we did not model the disk sizes as yet. So in the sense that we were assuming Shakura-Sunyaev disk to be true. So if the disk size is not, this disk model is not true, so what different models can we work on to explain the larger than this 3x disk size discrepancy? And then we were covering optical bands here only because of ground-based telescope. So now we want to map the inner accretion disk also and the corona at the top of the disk. So for this we have proposed using AstroSat. So we will be observing this thing maybe in a couple of months from now. So this will also enhance our understanding of the innermost regions of the accretion disk. So that's it. Thank you. So if you have any questions, please do let me know.
So, it was a great talk. So, any questions from the audience?
Vivek, you talked about this SS this model, right?
Yes.
So, can you just briefly tell us what are the basic assumptions of this model?
Okay.
And how we can rely on the predictions of this model?
Okay, so what happens is that this model, it assumes, so this is basically a toy kind of representation of this model. So it assumes that your supermassive black hole is at the center, and then black hole is accreting mass. So what happens is that this the mass that is flowing into the black hole, so it will have some angular momentum, right? So black hole might not be stationary. So because the matter has to lose angular momentum, so it will form a disk. So this is basically a geometrically thin, optically thick disk. So this is why this disk
You are
exists.
taking this whole region to be a two-dimensional.
Yes. Because the h by r, so basically you can characterize disks by h by r ratio, height to radius. So h by r is very small for SS disks. So yeah. So and then we assume that disk reprocessing is there. So this is also coming from the SS disk assumption only. So what happens is that since black hole is accreting matter, so the innermost region will have the highest energies because of this interaction between particles. So the innermost region will be radiating X-rays, and then this X-ray will be reprocessed through the other regions. So other regions will lose some energy. So X-ray will be converted to UV. UV will come to optical. So this will radiate through that. Right.
So, I mean, just I'm not much familiar with this, but I was just getting one question out of curiosity.
Mhm.
People talk a lot about black holes, and my question is that is there some attempt which people are trying to think of this black hole microscopically, how we think of the things happening inside or near to the black hole? Microscopic perspective.
Okay. So what happens is
We
that
are thinking of, a small mass, very large mass concentrated in a very small region. And this is a layman interpretation of a black hole, right?
Right.
So how this large mass is concentrated in a small region, or what is the microscopic depiction of this?
okay. So
Or to what length scales people have been able to talk about this thing microscopically?
okay. Yeah. So
My question.
yeah, I understand your question. Okay. So the black holes that we are talking about in our context, so they are like supermassive. So they have million to billion solar masses sitting there. So this we can assume, this we can understand based on the velocity of the clouds and applying the Kepler law there. So we can get the masses there. So like you were saying, the small. So we have stellar mass black holes also. So stellar.
For example, my question is, because I work in condensed matter physics, so from a very general student of physics point of view, we think that mass comes from, say, nucleus. Then there are certain particles like protons, neutrons, right? Okay. In black hole, what actually is the form of that mass? Is there any kind of explanation or?
Well, that I'm not pretty sure
my
of that.
question valid?
I got
Does
your
it
question.
make some sense?
Of course, I got your question. But the thing is that it's from a particle physics point of view, I think they can answer it in a better way. So we are talking about in macro scales.
So I think, for example, we could be black hole is something as though is not known basically, but the constants, whether the matter will be completely doomed or not. Because that's unexplored, it is not possible because no information can come out of the black hole.
Exactly.
So,
Any
so other compact objects, for example, white dwarf or neutron star.
Yeah, so we have white dwarfs, we have neutron stars. So in fact, the stars that could not be, massive stars which were not capable of becoming neutron stars, they become black holes because of the concentration of matter inside there. So because we have limits there. So we have Chandrasekhar limit, 1.4 solar masses. So the Chandrasekhar limit stars will become white dwarfs. Stars beyond that will become neutron stars, and then even massive stars beyond. Yeah, so they will become black holes. So that's how they form.
They are something like supermassive, but in what form mass stays there is not clear.
That is not in because so the current understanding is that
Microscopic picture of how mass is sitting there is not clear.
that is not clear now. Yeah.
Maybe Suresh can say something.
So for example, in this context, people might ask you what is the size of the black holes.
Yeah.
So because you don't know whether.
Yeah. See, you are asking about how far we have been able to resolve.
Yeah.
Right. So in these kind of objects, we have been able to go up to, so black hole will have a Schwarzschild radius.
Yes, what's the meaning of that Spectral? That's what I was pointing. You
Okay,
mentioned that.
yeah, so Schwarzschild is basically the event horizon of the black hole. So beyond this, you cannot get any information.
What is the typical length scale?
So it's like, it's 2 gm by c square. So g is gravitation constant, m is your mass of black hole, and c is the speed of light. So you can estimate the Schwarzschild radius for your black hole.
Roughly how much this number turns out to be?
So for sun it will be like a few kilometers, if I'm not 3 kilometers, yeah. So for sun it will be 3 kilometers. So these are supermassive, so they will be very large. So in these objects we have been able to resolve up to 6 Schwarzschild radius based on the X-ray emissions, X-ray observations. So up to 6 Schwarzschild radius people have been able to go, but beyond that it's still uncharted territory so far.
So I think people might also ask that you said that it's very small size and its luminosity is also very large.
Very large.
So why do you think that it's only the radiation energy, not the nuclear fusion, for instance?
Yes, that is a good question. So why fusion is being discounted? Because of the extent of these regions. No, efficiency can be, but it can be agreed that okay, maybe. So the region is very small, no. It's like milliparsec. We have broadland regions, so it's very smaller than the solar system itself.
Right. Okay.
So at that space, if you have nuclear fusion going on, so
And probably you need basically lots of.
we need lots of fuel there because it has efficiency of 7% only, the fusion.
0.7.
0.7%. 0.7%, yeah. So while accretion has very high efficiency, so accretion can give rise to these luminosities as compared to the fusion.
So you can check if there is a question.
How do we find quasars?
How do you define quasars? Okay, very good question. So what happens is that quasars, they will look just like stars. However, if you look at the spectrum of these objects, so the spectrum will not be anything like a star. So they will not be like a star. It has a black body curve going on. So the quasars, they will not have a black body spectrum. So that is one of the ways to identify quasars. Another thing is that the luminosity of these objects is very, very high, and they are located very far away, so which we can get. Another thing is that they are multi-wavelength phenomenon. So you can observe them in X-rays, you can observe them in UV, you can observe it in multiple wavelengths, and they will be very bright in all these wavelengths.
Hello. So we have a question from Nalin Dhiman. He said, "Sir, you said it's highly luminous, but light can escape from supermassive black hole. So how is luminous? Or maybe I have missed something."
Okay. So I think light cannot escape from supermassive. This is what it means. Okay, so what happens is that the black hole is not releasing the energy. What happens is that you have matter spiraling onto the black hole, and this matter is basically being heated up because of the accretion onto the black hole. So this matter which forms the accretion disk, this is releasing the energy, not the black hole itself. I hope that satisfies.
So I think if we have less time, so I will ask one concluding question. Since you have reached the PhD now, I don't think you are going to stop. You might have a lot of plans. So what do you think? What are the kind of excitement you are going to get in AGNs and AGN fleets or Quasars and this? So what's actually happening? Is it right times? Or is this going? Curve is going upward or is it slow like this?
Okay,
So what
yeah.
are the kind of excitements you
Okay.
see
So the thing is that this reverberation mapping technique, it has grown by leaps and bounds in the past 10-15 years, and with this
and the surveys which are going to come.
Surveys, yeah, obviously. So LSST will be there, VRO LSST will be there, so it will have multiple band light curves. So that way we can understand. Another thing is that the variability mechanism is not very clear in these objects so far. So if we have, long light curves, so we can have some information about that also. But I think I'm more excited about this thing. I'm most excited about this thing because this has the potential to resolve your accretion disk. And once you get this kind of data for multiple quasars having different accretion rates, different black hole masses, different luminosities, so then basically you can build robust disk models and then try to get the prediction from these models. Because here, we are lacking in theory. The theory is predicting only this thing. So, yeah.
So one last question from Manish Pathak. What is the difference between quasar and black hole?
Quasar and black hole. Oh, okay. So quasar is basically a term used to describe an object having a supermassive black hole at the center. So basically a quasar will be hosting a supermassive black hole inside it. 1 million to 1 billion solar masses, 10 to the power 6 to 10 to the power 9. So I hope that answers.
So that's it.
So, okay, so yeah. Okay. Thank you.
So I would like to thank our PhD scholars, Professor Arkinson, Homchandson, and our PhD scholar and all the students who have participated via online mode. Thank you for your patience and for your attention. So, with these words, we will end this session. Thank you very much.